Okay, so we're going to continue on transistors and kind of background about transistors. And I had asked you to essentially design circuits that look like this one on the right hand side here and explain their operation. And at the most basic level, this is acceptable, okay? But in reality, transistors are quite sensitive devices and they will have to be protected from a couple of things. So let's talk about transistors. So the idea was that if this sensor's output voltage goes above 0.7 volts, then that transistor will saturate, and then the output device that's connected on the collector to supply will come on. So that would lead you to believe then that perhaps if you built a circuit that looked like this, where you had a bulb connected to a transistor, I want you guys to get into the habit of drawing this stuff, and you just put a switch in there like that, and connected the switch up to supply. It would lead you to believe that as much as it's not an automatic circuit, it's now a manual circuit, that would lead you to believe that that circuit would work. Now, is that the case? Let's get a quick look. So there's a supply, there's a transistor with a bulb on the output, there's a switch on the base. Let's get it wired up. Again, hopefully you guys have considered downloading this to do these types of exercises. You really should. It's free and it's very good. So the idea is now if I press that switch, that bulb should come on, but it doesn't, right? The transistor gets destroyed. And the reason the transistor gets destroyed is that, as I said, transistors are very, very sensitive. They're very, very sensitive to a couple of different things, and one of the things is that transistors are very sensitive to current sensitive. That means that we need to find a way of limiting current going into the base. Not in every instance. Sometimes a transistor circuit will work without us putting any control in place, but a lot of times we'll have to. Now then, you should already know about the relationship between voltage, current and resistance. If this is too high, how do we make it go down a way? So we could either reduce this, or so if I rearrange this equation, I equals V over R. If this is too high, how do we make it go down? We could either reduce this guy or increase this guy. Now the issue with reducing voltage is that, well, you might not be able to. If that was like a battery fixed, you can't change the voltage of a battery. So that leaves us, the only option is to increase resistance to reduce that, and that's where resistors come in. So we've already been introduced to resistors. There's a fixed resistor there. I should be able to drop that into that circuit, replace those damaged components, and hopefully this time, there we go, it works. Okay, so it now limits the current. So this is called base protection. Okay, it's not required in every instance, but if a transistor is failing, then very possibly base protection could be the answer. It should be one of your first stop shops, right? So the truth is that this guy would get destroyed in this setup. It gets destroyed. I'm flitting between using the pen to write and then typing. Okay, this is called a base protection resistor. The National 4 and 5, we're not going to worry too much about its value. 1000 ohms, 5000 ohms, whatever works basically. If you have to use one, put it in. If your circuit doesn't work, you can try reducing the value of the base protection resistor. Base protection resistor, what's it for? It protects the transistor from too much current, too much input current output, so that means base current from the sensor. So it's possible that if you think back to the sensors that we messed about with, don't know how many sensors that I have done in this particular presentation. I've done a lot. So in this one, that resistance there doesn't really have the opportunity to go too low. That's a kind of fixed resistance. So if that transistor can handle the current that's coming in through that resistance, because remember, the path of the current that would destroy the transistor must be through the top half of the sensor, because that's where the current's coming from, conventional current. That's where the conventional current is coming from the supply. So it's the value of this resistance that matters. If it was a light sensor instead of a dark sensor, then it is possible that the resistance of that LDR could drop so low that we would have too much current going in the base. So in light sensors and in heat and hot sensors, high temperature sensors, it's more likely that we'll need a base protection resistor. Okay, so that's one area where transistors need protected. They require base protection resistors. Okay, let's look at another area. So let's say that I give you a circuit that includes the use of it, and we haven't covered it yet, don't worry, but let's, I want to stick with transistors, so don't get bogged down too much in the detail here. Let's stick with a system that uses, again, we'll just stick with that kind of dark sensor idea. Why I feel the need to do sound effects sometimes. A transistor, and we're going to use a device called a relay. Now, you haven't used a relay before. You don't know what a relay is for yet, but they are going to be. We're going to be talking about them very, very soon. A relay is a device that controls a switch. And right now you would be correct in thinking, why on earth would we want to control another switch? The transistor acts like a switch. There is a reason, a very important reason, and we'll talk about it soon. But there's this relay, right? So if I build that circuit, the idea would be that when it's dark, the transistor saturates, the relay will energise, and that switch will change state. Let's build that circuit then. There we're going to use a relay. Let's switch back in there. I'm not sure we need that resistor. Hopefully not. And then what do we say, a dark sensor? So we'll stick that down there. And then we'll stick that resistor on there. Don't know what value that will need to be, but we'll get to the bottom of that soon enough. There you go. Okay. So hopefully, that value's going right. Oh, there you go. Oh no, what happened there? So the circuit seems to work at first. As light level drops, the relay energizes, and you see that switch change state. Look, hey! But then when the light level starts to climb again, and the transistor desaturates. Oh, didn't do that, did you? No, I did it that time. Yeah. Doesn't do it every time, but it will do it. Yeah. What's happening? Why is this happening? What's going on? Right, so we need a little bit of explanation. A little bit of explanation behind this device and devices that like it as well. Let's have a quick chat about these devices. Okay, so something you need to know about a relay is it is an electromagnetic device. Now you might not know what that means, and electromagnetism isn't part of the course, but it's an electromagnetic device. It relies on the principle of electromagnetism for it to operate. What's the principle of electromagnetism, I hear you ask? So the principle is that if you have a conductor, copper wire, ooh, look, copper. If you've got a copper wire and you pass current flow through it, you induce a current in it that way, what will happen is you will create a magnetic field around the conductor. So as soon as you create current flow in a conductor, you create a magnetic field around it. If it's just a straight conductor like that, it will be a weak magnetic field. And what people discovered was that if you took the conductor and coiled the conductor on itself really tightly, created a coiled conductor. Oh, your pen's giving up the ghost there, alright. Then when you pass current through that, you create a amplified magnetic field. Yeah. You strengthen the magnetic field around it. That's what an electromagnet is. And you can have like cores inside that coil that help direct it and focus the magnetic field. So there are some devices that we use that rely on this principle of electromagnetism. It's a very short list, alright? So the list of electromagnetic devices that we use goes like this. Motor, solenoid, relay. That's it. Those are the three electromagnetic devices. And it's that magnetic field that's causing us problems. But you notice it's not causing us problems when we go from no magnetic field to magnetic field. It causes problems when we go the other way. So it's when we switch it off that we have this problem. And the deal is, as I had mentioned before, if electron flow and magnetism go hand in hand. So as soon as you create current flow, you create a magnetic field. As soon as you remove the current flow, the magnetic field will fail, it will disappear. But here's the problem. The problem is that if you've got a coil like that with that kind of amplified magnetic field going through it, when you remove the current flow, the magnetic field won't disappear straight away. It takes a finite, a measurable period of time for that magnetic field to collapse. And because electromagnetism and current flow go hand in hand, while that field is collapsing, it will create a current flow in the coil of wire itself. So it's almost like that device, when you switch it off, while the magnetic field degrades, that wee guy becomes a source of current flow. And it's that current flow that destroys the transistor. This phenomenon is called back EMF. Okay, back EMF. This is what you need to know. EMF stands for electromotive force, the force that makes electrons want to move. So it's just a really fancy way of saying voltage. Okay, so what it's basically saying is when you turn these devices off, while the magnetic field collapses, the device becomes a voltage supply and causes current to flow. That's what's destroying them. So what do we want to do? How do we protect the transistor from that? What we do is we provide a wee short circuit. Now we can't just put a wire in. If you just put a wire in, then the relay will never work. It's almost like we need a one-way short circuit. So a one-way short circuit would be a diode, and that's what we use. Oh, what happened there? We stick a signal diode in there, not a light emitting diode. A signal diode. Come on, this is getting annoying. And Control Z. Here we go. Right, so what we're going to see now is when we turn it on, it works. When we turn it off, yay! And you can actually see a little kind of tick happen at the bottom of that diode there, as the diode handles the back EMF. Yeah. If I put a light emitting diode in there, chances are it would flicker. It would actually flash every time it stopped the back EMF from destroying the transistor. This is what this diode's for. This is another thing that the diode needs protected from. Okay, here's your second protective component. It's my, can't see my keyboard in the dark. So let's take that note. This diode protects the transistor from back EMF. Now, please remember that that's only true for these three devices. So if you've got an LED in the output position, or if you've got a light bulb in the output position, or if you've got a heating element in the output position, or any other device that's not one of those three, a buzzer, if you've got a buzzer in there, you don't need the diode. You only need the diode for those three. Okay, so that's the two protective components that we put around transistors. We put base protection resistors in if they're required, and we put diodes in across any electromagnetic devices to protect them from back EMF. So, with that in mind, what I want you guys to do is, I'm going to put up two circuits, two partial circuits, not complete circuits, and I want you to explain, and it'll be a bit repetitive, but you know, repetitive might help get it, drum it into your head. So I'm going to pause it, put these two circuits up. Right, so these are the two circuits that I want you to explain. So this one's going to self-explain, that's a potentiometer in the middle there. So as you turn that up and down, the light will go up and down. And this is auto blinds closer when it gets dark with solenoid outstrokes. That's obviously not the correct symbol for a solenoid, but Yenka doesn't have the correct symbol for a solenoid. So you have to explain what's going on here, obviously based on the content of this video. Right, okay. Make sure that your explanations are full and complete, and make sure you put them in your, write them out or type them out, I don't mind what one. Right, all the best.